Okay, 2 sections left to go. So looking at 3.5 today, we are now into solving log equations. So the first type we're going to be looking at is solving equations by creating common bases. This, of course, is only going to be doable in certain cases when you can create common bases, but it's kind of like one of the first things that we look for. So if you see this initial equation that we're starting with, before you try doing anything too creative, do the basics first. So, for example, I can start by just dividing 27 over to the other side, so 12 over 27, and then reduce it to get this. Now I'm looking to create common bases, right? Because there's nothing more I can do to simplify, but I'm trying to solve for an exponent that says x over 4. So what they did was they said, okay, well, if this base is 2/3, let's write this as 2/3 squared, right? So notice it's the same value, but by writing it this way, now this base is equal to this base. So what does that tell us? Well, I mean, this is an equation, so if the bases are equal, that must mean that the exponents are equal. So we're saying x over 4 is equal to 2, since the bases are equal, and then that gives us that simple little equation to solve, and we solve for x. So let's take a look at that on 2 of these. So same deal on this one. So we're going to start by just dividing that 24 over to the other side. So I got my 1/2 to the x over 3 power is equal to 12 over 24, which is already 1/2. So this one is super nice. We didn't even have to really create common bases. It just kind of fell that way within the process here. So think of this as 1/2 to the first power. So in order for this to be a true equation, if the left side equals the right side, if these are both the same, then the exponents must also be the same. So x over 3 is equal to 1, since that's the first power. And then that gives us that super simple equation to solve. Multiply your 3 over to the other side, and we have our value for x. And you can always check that by plugging that in, make sure that it fits. So take a look at this guy. Again, similar beginning to this. We're going to divide the 81 over to the other side. So I'm looking at my 2/3 to the x over 3 power. On the other side, I got my 16 over 81. And I would reduce that if it were possible, but that cannot be reduced. So the goal is, how can I write this to have the same base as this? So I need this to be 2/3 to some power. So in this case, since 16 is 2 to the 4th and 81 is 3 to the 4th, we can write that as 2/3 to the 4th power. Right, so I'm still keeping the exact same value that I had here. All right, this is still 16 over 81, but now I've written it in such a way to where these bases are the same. And if the bases are the same, must mean the exponents are the same. So now we can say x over 3 equals 4. Simple equation to solve to get our value for x. So that's kind of the path. When you can create common bases, it's a great way to go. Of course, there could be scenarios where you cannot create common bases. If this were, let's just say this was 15 over 81 instead of 16 over 81. There's no way you could have gotten it to look like this as 2/3. So in those cases, we're going to need other methods for solving. And we're getting into some of those methods here. So the next thing they're having us look at is, now instead of solving for the exponent, now we are actually solving the log equation. When you solve log equations, there can be a couple different approaches to doing these. I highlighted method 2 because this is going to be the most common and probably the most friendly method of solving. Tends to make the most sense to people. So what we're looking at on method 2, and this is, I'm sure, would have been the way you would have seen this in Algebra 2. If I have an equation like this, the main thing that we're looking to do is simply take it out of log form and change it into exponential form. So remember what that form looked like. We put that way back early on in our notes. Trying to remember what page we put that on for you. There we go. So back in 3.3, in part 1 we had this. So this is what it looks like in exponent form. Here's what they're giving us. So our goal is to take it out of this form and rewrite it to look like this. And notice the whole purpose of doing that, right, is to isolate that x when we put it into exponent form. So that's going to be the goal here. So on this one, they said, keep in mind this is a base of 10, right, because there's no other base written. So we are seeing this as 10 to the 4th power is equal to x to the 4th. So here's my 10 to the 4th power equals x to the 4th. And so by writing it this way, now we can go on to simplify. All right, so the one issue that you got to notice on this one is, in order to get this x by itself, we did have to take the 4th root of both sides. And you got to go back to basic algebra rules that anytime you take an even root on both sides of an equation, you always got to throw in the plus or minus. Right? So that's anytime you're doing an even root. So in this case, that's where we got the plus or minus from. So that's why we get those two solutions. One other thing that's kind of good to look at is they pointed out an incorrect method for solving, and they said, what if we use the power rule? What if I moved that 4 to the front, divided both sides by 4, and that put me here, and now changed it from log form into exponent form. So it became 10 to the 1st power equals x. Well, that's just 10 equals x. So why is that wrong to do? Well, it misses out on one of our answers if we do it that way. Okay, so that may be safe in some cases, but not in cases where the plus or minus was needed. So method 2 is definitely the best way to go in making sure that we get all of our answers. Keep in mind we can always check these graphically on our calculator. If you go back to the original problem, if I graph the log of x to the 4th as one graph, y equals 4 as a separate graph, and then look at where those two graphs intersect. They intersect right here at -10 and right here at +10, right? And so we can also see that those guys match up with the answers that we got by doing some algebra out there. All right, so let's try a little of this on our own here. So we're going to try this guy. So again, I just simply want to take it out of log form and put it into exponent form. Do not forget that there's an automatic base of 10 here if they don't put something else. So to switch this into exponent form, we're going to say 10 squared, so 10 to the 2nd power, is equal to 2x squared. So that puts us right here. So that's obviously 100. I'm going to divide both sides by 2 and get 50 equals x squared. So here's where I got to square root both sides. This is where the plus or minus comes in. So I'm looking at the plus or minus square root of 50 for our value for x. And of course we can simplify that in a couple ways. If the directions say something about rounding to the nearest 10th or 100th, we can put that in a calculator. If it just says write in exact form or simplest radical form, we can always take that step too. So we could have said this guy would be 5 root 2. If we wanted to go and keep it in exact form but simplify it, or we could go calculator and turn that into a decimal. So just follow directions on that. If the directions don't say, then you get to pick your favorite method. All right, a couple more examples I want to take you through here, and then we'll get to that next page. So for solving equations like this, notice for this one that we got one too many logs floating around over here. So one thing we can do on this is take these two logs, because they're both natural logs, so log base e, and condense them into a single log. So this just draws you back into what we did in our last lesson. So I'm going to take the left side of this equation, take those two logs and condense them, right? Because it's a plus sign, I know it's going to be multiplication. So I'm going to be looking at my 3x minus 2 times x minus 1 equals 2 natural log x. So that puts us here. And the benefit about, well, let me get to that in just a second. We could distribute that out. One thing I'm going to do first, though, is I'm going to take this 2 and bring it back up to here to becoming an exponent. using our power rule. So we're going to write it this way. So here's what you're going to notice on this one. Notice that both sides are the natural log, right? So if you have identical logs on both sides and there is nothing else going on here, we can simply drop the logs and keep what's left. And that's why I moved the 2 here first, because we need to see this as x squared, not 2 times x, right? And so, but at this point, now it's only the natural log of something on both sides, so I can drop the natural logs. So I'm going to cut those guys out. I'm going to distribute what I got going on right there. So what's that? Minus 3x minus 2x, so minus 5x in the middle, plus 2. Dropping that natural log, I get the x squared. So now we're back to just solving a basic quadratic. Let's subtract x squared from both sides. And then you can pick any quadratic method to solve from here. Something we are going to keep in mind, and this is what I wrote right here, if I'm checking for extraneous solutions, simply meaning that when I plug it back in, I got to make sure that it fits. So let's just talk about real quick before we finish solving this, what would be acceptable. So in this case, keep in mind that a log, and we saw this when we were doing our graphs, that a log cannot have a 0 or a negative. So whatever goes into these parentheses must be greater than 0. So I cannot have 0. And then based on these, I got to make sure that when I plug it back in, it doesn't create a negative solution. So that's something we got to check for after we solve. So you could go with factoring on this quadratic formula, whatever you prefer. I'm just going to do it over. I'm just going to factor really quick over here. So I'm getting factors of 2x minus 1 and x minus 2. So as I solve those, I'm coming out with x equals 1/2 as well as x equals 2. And so both of these kind of seem okay initially. Both are positive. Neither one is a 0, so that's not an issue for him. But let's just check and make sure they are okay if I plug them back in. If I take a 2 and do 2 minus 1, that's positive. If I put my 2 here, 6 minus 2 is positive, so he seems safe. What about that 1/2? The 1/2 is okay here. If I put 1/2 here, well, 1/2 minus 1 would create a negative value. You cannot take the natural log of a negative, so he is out, and I can only keep x equals 2 as my solution. Something you really have to watch out for and make sure that the answers that you're going to keep are okay if you were to plug them back in. So let me take you down. I just tried to lay out several different scenarios here for you to give you a bunch of examples to look at for this section, because that's one of the tough things about solving log equations is there are just a lot of different scenarios that we could come up with. So let me jump into this next one. Again, if it's in log form and there's only one log, all right, so this is different than the one I did up above. The one up above had a log on both sides, and so I could just drop the log. Not the case here. This one is only a single log, and probably your best method in all these cases is just going to be to change it from log form into exponent form. Keep in mind it's a natural log, automatic base of e, so if I change this into exponent form, we're going to say e to the third equals 2x minus 1. From here, if you were going to actually be solving for x and get the decimal rounded answer, you're going to have to put e to the third in a calculator. You can be asked to keep things in exact form, so that's why I'm going to do it for now. This would be an irrational number, so the only way to go beyond e to the third would be to plug that in your calculator. So I'm simply going to add 1 to both sides and then divide everything by 2. So it's going to look like this. So I added 1, divided everything by 2. And so this is a great way to leave your answer. We could split into 2 fractions, but I don't think there's any benefit in that. The only thing you'd really do beyond this would be to put it in your calculator if you wanted to actually get like the decimal answer for this. On guys like this, now we are solving for an exponent. So typically when it is in exponential form, and we were solving for that exponent, great path would just be to change it from exponent form into log form. Remember, the whole purpose of a log is to isolate the exponent. So by putting it into log form, I can get x by itself that way. So on this one, we're going to say log base 0.7 of 2.5 is equal to x. And so from here, if I wanted to, again, this is as far as you're going to go without a calculator. If you want to put this as a decimal, you would simply have to type this into your calculator to get the decimal version for x. Similar thing on this guy. The only difference is before I convert to log form, I need to simplify everything that I can do first. So the general rule is you want to isolate the term with the exponent before you change it into log form. So I would start by subtracting that 5 over. Putting me here. Divide both sides by -3. So I get this. Now we can look at changing this into log form. Because it's a base of e, I'm going to use natural log and say natural log. See, my base is always my base. The 4/3 comes over. And it equals -x. So we get that set up right here. And again, I could divide both sides by -1, get that x by itself. So I'm going to divide both sides by -1 and get this. It's my way of not having to rewrite that again. So at this point, if I wanted the exact answer, that's as far as I can go without a calculator. If I wanted to, I could put all this into my calculator and get the decimal version for x. Let me take you down to this guy. On this one, similar to what I did up above, I'm going to take these two logs, combine them to a single log. Before I do that, I'm going to take this 1/2 and put it right there back as the exponent. So that it looks like this. Now I can take those two logs and condense them. Remember, this is subtraction, so we're using the quotient rule. The positive one goes on top. The negative goes on bottom. So square root of x plus 4. And you could have left it as a 1/2 power. Okay, so all I've done so far is take those two logs and combine them into a single log. Now that I have a single log equation, now I'm back to saying, well, let's just change forms. I'm going to take it out of log form and put it into exponent form. So my base is 10, since there's nothing else there. So 10 to the first power, which is 10, equals x over the square root of x plus 4. Puts me here. And at this point, I am going to need to multiply this over to the other side, but I also have to get rid of that radical, and I'm going to have to square both sides. So I'm going to start by just squaring both sides. So that left side is going to become 100. My right side, if I square that whole fraction, I get x squared on top. I get to drop the radical from the bottom. Puts me right there. Now I'm going to multiply the bottom over to the left. I'm going to move up here, give myself some room. So 100x plus 400 equals x squared. Back to my basic quadratic. So let's get everything onto one side, make it equal 0. Always want my leading term to be positive, so I'm going to bring those two over to the right so I can keep my x squared as a positive. So that puts us here. Now we are looking to factor if possible. Let's see, is there any products of -400 that add to be -100? So not factorable in this one. You'd have to maybe use a little quadratic formula. I threw it into my calculator and got those two solutions. Notice which one you can or cannot keep here. So definitely cannot keep the negative. Would not be okay here. Even though it would be okay here, it fails this one. So you cannot keep the negative answer. We're just going to keep the 103.9-ish as our only solution. And the last thing that we're going to go over is this guy right here for example 7. I want to show you something out of your book really quick on page 290. So I wanted to show you this little formula, and you're going to see this in our notes as well. Whenever you see these little sigma notations, these are all like things you'll want to know leading to calculus. So that's why I try to point out these types of things as much as we can. But anyway, this is a little formula for Newton's law of cooling. So one thing I wanted to point out on this formula is, remember this would act as like a vertical shift. So if you think of our basic layout for an exponential function, the guy that is being added or subtracted as a constant is our vertical shift. If you think of a basic exponential function, remember that in the parent function, you have a horizontal asymptote at x equals 0, right? And that horizontal asymptote is what your graph would be approaching as x increases. So as x approaches positive infinity, or as your x approaches positive infinity, your graph is approaching that horizontal asymptote. Well, if you have a vertical shift and your graph shifts upward, so would your horizontal asymptote. So that's why this little equal equation down here, that's what it's talking about. It's saying the limit of your function as t approaches infinity, as time gets bigger and bigger and bigger, or as x gets bigger and bigger and bigger, your graph is going to approach this value. And this value is the vertical shift, right? So that would be where your horizontal asymptote would go, which is what your graph would be approaching, which is why that is the limit of your function as t gets bigger. So these will be pretty simple because all we really have to do is plug in the information. So like we're given a formula and all we have to do with this is plug in the numbers. So they're giving us like an initial time that we're seeing right here. So time sub 0, what is our value? Right, it's 96 degrees Celsius. That's what they're telling us right here. So that's our initial temperature. The T of M is the temperature that it's being placed into. So if the water that I place this item into is 16 degrees Celsius, all right, so here's like what you would call like the, I don't know, your overall temperature or your room temperature. But that's what this smaller item is being placed into. That's our T of M. So that's why your T of M is the limit, as well as your horizontal asymptote, right? If you put this tiny little egg, even though it's super hot, if you place it into a very large container of cold water, these two temperatures are going to mix, right? And so it will affect the temperature of the water, but only slightly, because the water is much more mass to it than this tiny little egg that we're placing into it. So the water is going to have a bigger effect on the egg than the egg would have on the water. So even though these two temperatures are mixing, he is going to get closer to this temperature rather than him getting closer to this temperature, right? So what you're seeing as part of this formula is the difference in those two temperatures, right? So your temperature of the egg minus this overall temperature that we're placing it into becomes the base, or sorry, our leading coefficient within that formula, right? Our base is E that we have right here. So that's where, and then if you clean it up, it looks like this. And then we're going to be solving for that K value. Then we could apply it to any length of time that we want to. So let's just go through the one that I have for you on this. So I kept the formula in here so you guys could see that. All right, so real similar to the one that we were just seeing on there. They're giving us an initial temperature. We have this hard-boiled egg that's 97 degrees. So that's our T sub 0, right? So that's what's going in for T sub 0 right here. We have the overall temperature that it's being placed into. That's the 17 degrees. So that is this guy as well as this guy. And so if I just do some basic cleanup on that, here's the equation that we're going to be solving. They're giving us a little more information so that we can solve for K, right? That constant of variation that we have. When you have an equation like this and you solve for K, the constant of variation doesn't change, right? So once we figure out what that value is, K will forever be that value no matter what other numbers you plug into this formula. So it's kind of like, that's why we need to know that first to figure out what that constant of variation is. So here's this equation that we're solving. So they told us some extra info. It says 3 minutes later, the temperature of the egg was 48 degrees. Right? So 3 minutes later, it was 48 degrees. In other words, if t is 3, right, 3 minutes, the result, it will equal 48. And so that's what you're seeing right here. So we're plugging in our information for time, the 3 minutes. Here's the new temperature that it's going to become. And now we're solving this equation. So now we're back into solving our basic log equations to do something like this. So remember we said, as we were doing this earlier, we said simplify whatever you can first. So subtract your 17, divide by 80. First thing we need to do. So if I subtract that 17, brings us down to 31 over 80. So that's the first thing we got. Equals e to the negative 3k. Remember, the entire purpose of logs is to get an exponent by itself. So that's the only way for me to isolate this guy, is to change it from exponent form into log form. So I'm going to use a natural log since my base is e. So natural log of e, base e, that brings the 31 over 80 to this side, isolates my exponent, which is what we were trying to do, and then of course I'm going to divide this by negative 3 to figure out my value for k. So that's what I did right here. So we're getting about, I'm going to say 0.316, try to keep that fairly accurate. Alright, so now that we know our value for k, we know our constant of variation. That's this guy within our setup, right? So for now I can plug in any amount for time that I want to plug in. So now we can either plug in time or solve for time. So the final question was, now that we know what k is, use this law of cooling to determine how long it's going to take for the egg to get down to 20 degrees Celsius. So remember, started way up here, we'd be putting this cold water. So this egg is going to get closer and closer and closer to this value as time goes on. So how long is it going to take to get to 20 degrees Celsius? So which means, now that we know our value for k, I can take this equation, I can plug in this value for k, and I can set the whole thing equal to 20 and solve for time. Right? So now we're just solving this equation, trying to figure out what our time is. So I would still start by subtracting the 17 and dividing by 80. So you're going to get something like this. I already know my value for k is 0.316. And we are solving for time. All right, so here's our setup. We're right back into switching into natural logs again to isolate my exponent. So I'm taking the natural log of 3 over 80. And again, I'm using natural log since my base is e. Isolating the exponent. So there's our setup there. All I have to do is one last step, divide both sides by negative 0.316, and I'll have my value for time. And so that would tell me then how many minutes. Should come out to be something like this. So that tells me how many minutes it's going to take for this egg to get down to 20 degrees Celsius. Keep in mind, if I did want to convert this into minutes and seconds, so instead of saying 10.39 minutes, you could simply multiply your 0.39 times 60 and convert it into minutes and seconds that way. But that is it for section 5. Only one more to go.